our friend John Cricket is back with 13 tips to make your code reviewer love you. Review your own code first. I think this is probably the most junior mistake ever. And for the record, I am not a senior engineer. I'm a mid-leveler, if you can even call me that. But when you first learn to code, you pretty much never like read your own code unless like there's a bug. Once you get it working, you pretty much never look at it again. And that's kind of the opposite of what you do in the real world. I didn't make this mistake too many times where you don't really look at your code and maybe you leave because it's kind of embarrassing from the start, which is really not that difficult to. Then you should add comments. But at the same time, ones, and it's justified because a big change of what that code is doing. And then if you actually wanted to change something, make it clear. Like you don't really valuable. When somebody more senior than you tells you, hey, you just made a mistake here, I find that super, super valuable, not just when it came to code reviews, but even with YouTube comments. Like if somebody points out a technical mistake that I make in a system design video, a leak code video even, which sometimes I make a mistake, it's super, super didn't have the full context on that. If you disagree with your reviewer, I think it's perfectly fine to explain your reasoning. Any type of critique or response should always be justified. You can't just say like to a junior developer, or even when you're arguing back to a more senior developer, you can't just say like, well, I feel that this is better. You have to give at least some kind of technical reason why. In the case of somebody gives you a 2,000 line pull request, you can't just tell them, I don't feel like reviewing it. You have to tell them it's more likely to have bugs if you give me a really big one. But if you make it smaller, I'll be able to read it better. Even if the truth is you just don't feel like doing it, that's still a technical reason. So try not to get too emotional, I guess, in code reviews. Try to keep it objective and have reasoning for everything. Communicate your responses explicitly. I think that goes with what I just talked about. I guess actually another point, that comment, how I was working with somebody who would send me some pull requests and I had to review them. If somebody leaves a comment telling you to do X, Y, or Z, and then you respond with the changes, you 100% should address that comment. You have to leave a comment saying, okay, this issue has been addressed, because otherwise then you have to go and look at the code. And of course the reviewer should look at the code, but if you come back to a pull request in the future, you don't really have the history, like whether you're gonna make a change and address a comment or you're not going to address that comment, you have to leave that history there, probably within the pull request. Why front end doesn't give you interest? Do you still have respect for those of us still interested? Yeah, I definitely do. Front end stuff. Yeah, like the UI of this was probably just as hard as doing the back end, but it's just not super interesting to me. And there's a lot of complexity in front end stuff that I don't know about. There's a lot of different ways of rendering stuff, a lot of different techniques. I don't know what exactly it is. It's like CSS obviously isn't interesting. Formatting blocks on a page like HTML isn't super interesting. Like knowing all the different ways of doing CSS like Tailwind, it's cool, but not interesting to me. JavaScript as a language, I just don't like it. I don't like the fact that it's not statically typed. Even with TypeScript, it's not really statically typed. Doing UI features, it just feels like copy and paste. Like you already know what to do. Like I want to make a menu like this. Like I coded this menu. I want it to collapse. I want it to open. People who are like visual, they like coding stuff like this. It's cool to them. I think it's cool as well, but like I would rather do really low level stuff. My first language was C, and that's why I'm kind of, obviously I wouldn't code when you're doing back end or low level stuff. I like math. Low level, obviously I wouldn't code like a back end server in C. It's been fun. Like I enjoyed doing operating systems. Those were my favorite classes in college. Creating a lot of like data structures and algorithms. And you don't do a lot of that in front end development, but more so you do it in back end or low level stuff. I like math. I like anything that I get to do math with. Outside external dependencies. For example, to solve a problem in web development isn't really about putting tools together so much as it is about finding the correct dependencies, the good libraries, and once you've found them, then putting it together is pretty easy. Not only is that not fun for me, but it's really boring and sometimes super tedious. It's like searching for a needle in a haystack. I'm going to give you two examples. A year ago, I made this roadmap thingy, and people always ask me, how did you build it? Because they're trying to build something similar. Like this thing kind of drags around. It's like a graph, it's like a tree. I'll tell you, it was pretty easy because I used a library. But first, I had to find it, and this is the one that I found. I'm using Angular. I tried to find the best graph library that I could in Angular. It took me a lot longer than I'd like to admit, but eventually I found this library. And then I went through the documentation and figured out how to make these like custom template nodes and then suited it to my needs. So this one's not a big deal. It was just kind of boring implementing this, whatever. Basically, it feels like instead of actually programming, I'm just going on this weird scavenger hunt looking for the code. Fortunately, it wasn't. I had to start fiddling around with Webpack because I was stuck in dependency hell. I couldn't get it to work. I had the same issue described. I didn't really figure it out. I didn't really feel like I learned anything. You're not really using a lot of external dependencies. Our friend John Cricket is back with 13 tips to make your code reviewer love you. Review your own code first. I think this is probably the most junior mistake ever. And for the record, I am not a senior engineer. I'm a mid-leveler, if you can even call me that. But when you first learn to code, you pretty much never like read your own code unless like there's a bug. Once you get it working, you pretty much never look at it again. And that's kind of the opposite of what you do in the real world. I didn't make this mistake too many times where you don't really look at your code and maybe you leave like an extra print statement or just something is messed up, like formatting and things like that. Thankfully, I didn't make this mistake a lot, but I've seen other people make it a lot. I've worked with people on NeetCode.io where I've had them do like really, really basic tasks for me. And it's so obvious that they don't even look at their own work before sending it to me. And it's just kind of hilarious. I worked with somebody who was working with me for over 6 months, and every single time, almost every time, they would have very, very trivial mistakes. So please look at your own work before you send it to somebody else, because it's kind of embarrassing if you leave silly mistakes in there. Write a clear change list description. Most of this entire list is not really a skill issue. It's not like a skill diff. It really is, in my opinion, just about putting in effort. I
Having solved more than 1500 lead code problems and having cleared interviews at companies like Amazon, Google, and Microsoft, there are things I have learned that if you already know a programming language well, stick with it. Basic syntax and concepts like loops, conditional functions, and basic input and output. Basic input in big tech interviews? The answer is no. As long cheat code problem, you should have some idea about computer science fundamentals such as time and space complexity, as well as basic data structures and algorithms. You don't need to go very deep since most of the learning will happen while solving coding challenges. But make sure you are familiar with how to calculate time and space complexity of an algorithm using big O notation. Learning big O notation will help you improve your algorithms and better understand why your algorithm may be running slowly. Once you have a grasp of big O notation, familiarize yourself with to implement basic concepts tags, queues, and hash map, and learn basic algorithms such as sorting, searching, and recursion. You don't need to know advanced concepts, structures. This approach will help you gain a deeper understanding of views differs on lead code. Don't spend too much time on highly disliked questions. They will drain your energy and demotivate you. For similar platforms, you can choose curated energy and demotivate you. Sometimes spend too much time on highly disliked questions. They will you need to solve more problems. In general, 3 minutes of focused effort to a problem. Answer is to learn patterns. Instead of focusing on individual questions, concentrate on identifying patterns. On lead code, you will come across multiple problems that follow a similar pattern. Once you know how to solve one of them, you can apply the same approach to solve others. For example, a common lead code pattern is to memorize the solution. So you need to practice in a time.
Any tips regarding getting first internship? You have to be good at what of these, but this is if you're looking for an internship, free labor. Can you? But it's very, and again, before you can prove it, you actually have to.
Lead code is hard, not only because it's hard to be good enough to solve. In that list, I will go to the second list and now start practicing. There is a roadmap that exposes you to the most common questions. So when I was asked a question on trees, it was virtually identical to a common tree question I've thoroughly solved before, and so on. But often will also include some of the high-level
Welcome to trees, and we have already seen a tree in this course. It's a linked list. So a linked list is just a tree that doesn't fork, but it is actually a form of a tree. So we'll use this as the starting point for creating the tree for this section. Remember, this node looked like this. So I'm going to put this back. And then we'll turn this into a node for a binary tree. So the first thing I like to do when we move to a new section for each data structure is have a different color. So a binary tree is going to have two arrows like this, and it's going to look like this: value, left, and right. So let's move this back, and let's build out a small tree. So this node, of course, can point to other nodes. So if you have something like this, you can think about it as dictionaries like this. That's essentially the same thing, except this is a lot easier to look at. So the way we've designed our nodes with value left and right, they're set up where they can only point at two other nodes. Designed this like this. That's essentially the same thing, except this is a lot easier to look at. So the way we've designed our nodes with value left and right, they're set up where they can only point at two other nodes. So if you set it up that way, it's going to be a binary tree, but trees don't have to be binary. You could have this point to 3 nodes or 100 nodes, or have it where you could point it to unlimited nodes. But for what we're going to build, each node can only point to 2 other nodes. And then, of course, these new nodes that we've added can also point to 2 other nodes themselves. So now let's look at some terminology. This tree here is what is called full. In a full tree, every node either points to 0 nodes or 2 nodes. So if you do something like this, now you have a node, the 7 node, that only points to 1 node, so it is no longer full. So let's remove that, make it full again. And if we remove these two, it is still full, but it is also something else. It is perfect. With a perfect tree, any level in the tree that has any nodes is completely filled all the way across. So this is also a perfect tree. But if we remove these two, it is no longer perfect, but it is still full. So let's bring these two back. So a perfect tree is also something else. It is complete. So with a complete tree, you are filling the tree from left to right with no gaps. So if we add a node down here, it is still complete because we are filling the tree from left to right. But it is no longer full, and it is no longer perfect. If we add one more node like this, filling this from left to right, it remains complete, but it is now also full. But it is not perfect because we haven't filled it all the way across. So if we do this, now it is full and perfect and complete. Okay, so let's focus in on this tree, drop some of these off. So this node here is a parent of these two child nodes. These two child nodes, because they share the same parent, are also called siblings. And every node can only have one parent. So if you see something like this, where a node has more than one parent, then it is not a tree. So let's put this back. And child nodes, of course, can also be parent nodes. Now these nodes at the bottom, they don't have any children, and a node that doesn't have children is called a leaf. All right, that is our intro for trees.
So in this problem, we're given a binary search tree and we are supposed to find the lowest common ancestor of two given input nodes in the binary search tree. And so the lowest common ancestor is basically defined as being the lowest node in the tree such that P and Q are descendants of this node, or P or Q happens to be equal to this node. So basically, what we're saying is 6 can technically be a descendant of itself. So for example, in this example, we're given P equals 2, Q equals 8. So we're going to start at the root because the root is always going to be a common ancestor of every single node in the tree, right? That's just kind of basic, right? For this node and this node, of course, this is going to be a common ancestor. It's not necessarily the lowest common ancestor, but it is a common ancestor. So what we're going to see is P is less than 6. Therefore, it's going to be in the left subtree, and it actually happens to be a direct child of 6. 8 happens to be greater than 6, so it's going to go in the right subtree. So basically, if we went in the left subtree, 2, is 2 going to be a ancestor of 2 and 8? Of course not, right? 2 can't be an ancestor of the node 8 if it's in a different subtree. Similarly, 8 is not going to be a common ancestor of 2, so basically if we look at this level or if we keep going down, we're never going to find a common ancestor between 2 and 8, so the lowest one that we found ended up being 6. So we notice if there's a split between the nodes that P and Q are going at, if they're going in separate subtrees, where that split occurs is going to be the lowest common ancestor. So if I change this problem slightly and I gave P as 7 and Q as 9, we would once again start at the root because we know this is going to be a common ancestor of these two nodes. And so now we're going to check, okay, 7 is greater than 6, right? And 9 is also greater than 6. So therefore, we don't need to search in separate subtrees. We can just go to the right subtree to look for both of these values. We know that this is not going to be the lowest common ancestor. This could potentially, though, be the lowest common ancestor. So now, once again, we're going to repeat that. We're going to say 7, that's going to be less than 8. So for a 7, we're going to have to look in the left subtree. 9 is greater than 8, so for that, we're going to have to look in the right subtree. So since this is where the split occurred, that means this is going to be the lowest common ancestor for this input. So we would return this node as the lowest common ancestor. So one last case is if we changed Q to be a 6. So once again, we would start at the root, right? Before we were checking if P and Q were both greater than 6, then we look in the right subtree. If they're both less than 6, then we look in the left subtree. If one of them is in the right subtree and one of them is in the left subtree, that's how we know this is the lowest common ancestor. But what about the last edge case where one of these nodes happens to be equal to the root node? In that case, this is potentially the lowest common ancestor. It's definitely a common ancestor of both of these, but now if we go lower, for sure none of the descendants of this node, nothing in the left subtree or in the right subtree is going to be an ancestor of this node itself, right? So basically, if we ever reach the node itself, for example 6, then that's going to be the lowest common ancestor. So it's an ancestor of itself, and it's also an ancestor of 7, which can be found down here, right? So this problem isn't too difficult once you can kind of understand that if there's a split between these two nodes, then that's going to be the LCA, the lowest common ancestor. And since we're doing it this way, we don't have to visit every single node in the entire tree. So the time complexity is not going to be big O of n, it's going to be log n, because we're only going to have to visit one node for every single level in the tree. So basically the time complexity is the height of the tree, which is usually going to be log n. And the memory complexity is just going to be big O of 1 because we're not really needing any data structures or anything like that. That being said, let's jump into the code now. So as I mentioned, we are going to start ourselves at the root node, and we're basically going to continue until we find our result. So we're guaranteed to find a result. P and Q are guaranteed to exist in the input tree. So what we're just going to say is while current is not null. Now it's never going to be null because we are going to find a result, but this is just a way to get it to execute forever until we find that result. So one case would be if the P value and the Q value were both greater than the root value or the current value that we're visiting, and in that case we would have to go down the right subtree. So since we're going down the right subtree, we can update our current pointer to current.right. Now the else case is basically going to be the opposite of this. So I'm just going to copy and paste that. Basically, if both of the values happen to be less than the current node that we're visiting, in that case, we would want to go down the left subtree. So in that case, we can update current and set it equal to current dot left. Now the last case is basically if our split occurs or if we end up actually finding one of the values P or Q. And in that case, it basically means we have found our result either way, so we would just be able to return current itself. Now, we don't have to put any return statement outside of the loop because we're guaranteed that this is going to execute at some point. So as you can see, this is a pretty efficient solution. So I hope that this was helpful. If it was, please like and subscribe.
Annual open source did specifically for the topic you just learned, and you're asked questions to explore. Enroll today, and I'll see you in class. Of the basic worker machine, and that is where containers will be launched by Kubernetes. Where is the information about the members? When you install Kubernetes on a system, you're actually installing the following components.
Hey everyone, Cy Venom here with AWS. Now, if you've seen my videos before, you'll know Kubernetes is a great way to run containers at scale. But a lot of you might be wondering when to take advantage of a managed Kubernetes service from a cloud service provider. Of course, today we're going to be talking about EKS, Elastic Kubernetes Service from AWS. We're going to be diving right in, so if you do need a refresher on Kubernetes, be sure to check out my Why Kubernetes video. All right, let's dive right in. With a managed service, what cloud service providers are doing is managing some of the undifferentiated heavy lift for you. This isn't special work, it's just work that needs to be done in order to maintain a highly available and secure, scalable environment. Now, EKS is no exception to that. EKS manages one pretty vital piece of the Kubernetes architecture for you. That's going to be the control plane. So I'll sketch that out over here. Now, today we're going to keep it simple. We're just going to call it control plane, but just know that this includes a number of components, kube components, etcd, the API server. Essentially, it's handling communication between you as an operator, the cloud service provider itself, AWS, as well as the data plane or worker nodes, which is where your containers actually live, which we haven't sketched out just yet. Now, the critical piece about the control plane is that it's running in an AWS VPC, not a customer-controlled VPC. So AWS is going to handle things like the backups and the scaling and the patching and the upgrades of this environment. And so as your workloads scale up, this is going to scale up to handle that as well. So this is a piece that you really don't need to worry about. It's that undifferentiated heavy lift, and AWS will really manage this piece for you. So the control plane is going to be able to communicate with the data plane. And this is kind of the critical piece that as a customer you need to be focused on. And this is going to be running in your VPC. And essentially what this means is that you'll need to spin up some compute, and then you'll have more control and access over that environment. So let's talk about that. Let's talk about the compute, because before we have that, we can't actually run any containers. Can have a control plane, but it won't know where to run the pods, the containers themselves. So looking at your VPC, let's say we decide to spin up some nodes. Now, there's a couple of ways to approach this. I'm going to start with the way that's a little bit more complex. That's going to be self-managed nodes. So let's say we're spinning up some EC2 nodes here. And there's a number of considerations I'll need to take into mind here. Things like the AMI, the Amazon Machine Image, essentially the operating system and some components that let it work with EKS. I'll need to register these nodes with the control plane, give it the right permission so it has access to access the workloads running within the cluster, within our VPC. In addition, we're going to need to do things like patching and upgrades and scaling. So you can imagine there's a lot of automation that I'll need to build here. But luckily, there's an easier way to do this. It's called managed node groups. So EKS has basically extended their API and has now given you a way to manage and spin up. Essentially, it's a provisioning and lifecycle management of the compute, the EC2 nodes, and you can streamline them with single API commands and operations. So for example, creating the node group itself, scaling it up and down. Another one that I want to mention here is that it comes automatically with a EC2 auto scaling group. Now, of course, we won't run the security patches and upgrades for you, but we'll give you a streamlined way, a single API call that you can simply call to make that upgrade go through. And this can really streamline some of that operational overhead of maintaining the individual nodes. Now, I should mention here that when running in AWS public cloud with EKS, you can go with EC2 or Fargate. Fargate is the serverless approach to the compute for customers that don't want the operational complexity of managing individual nodes, even in managed node groups. Fargate can give you that serverless approach. Of course, there are servers. AWS just manages them for you, giving you the right size compute for your workloads, reducing some of that operational complexity. Now, of course, for EKS running in hybrid environments, let's say on premises or on the edge, you can take advantage of EKS on Outposts or EKS anywhere. Check out my video where I talk about those two in a little bit more depth. Okay, so we've laid out the control plane, the data plane, the worker nodes, and now we have a way to be able to execute commands against the cluster. You know, I can use something like kubectl to run commands and deploy pods and containers, the standard Kubernetes environment. One thing I should mention here is that EKS is certified Kubernetes conformant. Essentially, it means that, you know, as we're using an upstream version of Kubernetes, we pass all the conformance tests, and long story short, whether you're running Kubernetes workloads on premises or in another environment, another cloud service provider, you can bring them to EKS with little to no code changes. I think that's some of the magic of using Kubernetes on top of AWS, this open source platform where there is a large community backing it. Okay, so how do we actually create something like this, right? How do we create these nodes, the compute, the control plane? Now, of course, the control plane itself is pretty easy to use the UI to do something like that. Now, let's say I want to do something a little bit more complex. Let's say I want to spin up the actual compute, the nodes, so I'll need to make some decisions like how many nodes, what type of nodes, that kind of thing. And so to do that, let's say I want to use a CLI. So use something called EKS-CTL or EKS-Cuddle, whatever you like to call it. But there's one more approach I want to talk about. And of course, I'm not limited to these three, but I do want to focus on these. Terraform. And Terraform, I think, is a very popular way in the community to manage infrastructure as a whole. It's an open source infrastructure, maybe something a little lift with things like managed node groups. As customers are building containers and workloads on EKS, they realize they'll need to integrate with AWS in a number of different ways. Carpenter with a K. It's a great open source project built by AWS that we contributed to the community that essentially enables you to better optimize additional nodes coming up. Hey everyone, Sai Venom.
In this video. We'll go through what is EKS, how to use it, and the actual demo of creating a Kubernetes cluster with EKS the easy way. For a quick overview, AWS is one of the most popular cloud platforms which has tons of services for different use cases. And EKS, Elastic Kubernetes Service, is just one of those many services. So what is EKS? It is a managed Kubernetes cluster, meaning AWS will manage the master nodes for you. It will create the master nodes, install all the necessary applications on them like container runtime, Kubernetes master processes in Kubernetes. EKS. In order to create the cluster with EKS, there are following steps involved. Before you even create a cluster, you need to do some setup or preparation. First of all, obviously, you need to create an AWS account. There is a free tier for 1 year when you're a new user, so you can take advantage of that. Then you have to create or have a VPC. It's basically your virtual private space in AWS, basically a space where you do your own stuff. It doesn't interfere with other AWS users in the cloud. That's basically what VPC is. Then you have to create an IAM role with security group. These two terms, in my opinion, are too obscure. So here's the human translation for you. You have to create an AWS user with a list of permissions. Permissions to create and do stuff with EKS service. Once you have these things set up, now you can go and create the control plane of the cluster, meaning the master nodes. You create the cluster with the AWS role or this IAM role, which obviously has to have a permission to create and configure the EKS cluster. Here just choose some basic information like name of the cluster, which Kubernetes version you want, which region your cluster should run in, and so on. You set some security for your cluster, and note that you can do this setup or creating the cluster to resources your EC2 instances from your local machine. You just want to create a cluster and start deploying your containers inside as fast as possible. Not an AWS tool, it is from Weave using EKS control. So with that, let's tool. And as I mentioned, it's from Weaveworks. So we're gonna first install the Weaveworks homebrew. And as you see, it's also in. This means before you can execute this, and command for that is EKS control create cluster. And this command would actually be enough. This will create a cluster with all the defaults, but we can also define a region. Usually it's the one that's nearest to you. So I'm quickly its type, different types depending on how much resources this is worker node created all the subnets and VPC and all this stuff in the back. Go back, appearing here. So this will actually take. So one thing to note here with the AWS, so maybe to note so that you know. So if I go back again and I refresh this, see cluster active, and there's some data that we should see them here. And this part will also take some time. So if I go back, let's refresh this. That is generated. This is the cluster that execute. So basically we're using kubes just right now. If I'm done with a cluster, for example, if it's a test cluster, as well as for my EC2 instances. So everything is terminating, deleting. You don't have to interfere and do anything manually, which is good. But as I said, this process takes some time. So to recap, we went through what.
Hello and welcome back. In today's video, get a name and create the role. And in addition to that default permission, we are going to add another permission. Go to attach policy. And this is a.
Hello everyone, my name is Abhishek and welcome back to my channel. So I've created a pod.yaml and I've deployed the pod.yaml using the kubectl. So what happened is my application is
I can say with confidence that continuous delivery as a software development approach works better than any alternative that I've ever tried or seen. And I've tried most of them. It doesn't matter what kind of software is delightful for me, of tens of thousands. It's provocatively titled and opinionated, replacing process dogma with engineering to achieve true agility. How did Walmart go from sometimes less frequent than annual releases, starting with just one of many multi-million line code legacy? If you optimize failures than they had before the transformation, the architecture of this system spaghetti would be a dire insult to pasta. Fairly early on, the group got inspired by my book, Continuous Delivery, and decided that that was what they wanted, and to achieve it, they realised that organisational until they were organised around small place limits on each team, then started to work to better about how to proceed and work. It is instead an engineering process that forces us to address the mistakes that we have made previously, and that even when our system is down and bleeding money. Because in reality, that's when we most need the protections that our deployment pipeline has automated. Making the deployment pipeline definitive for release, whatever the nature or cause of the release, is another of those important disciplines that helps us to see the wood for the trees and focus on what really matters. That our changes are safe and we're not going to make things worse. This then forces us to optimize to reduce the cycle time. giving us fast, clear, definitive feedback at every step in every context. But for that to be definitive, it forces yet another discipline on us. We must evaluate deployable units of software, because otherwise we're only guessing. So again, the work that the Walmart team did at the start of establishing sensibly autonomous teams with better bounded services and components adds extra value, because their work is not technically or socially coupled and dependent on other things. They can make changes in the confidence that if all of their tests pass, they can release those changes without any more work.
Today, we're diving into the world of webhooks and how they stack up against old school methods like long polling and short polling. If you ever run an e-commerce website or dealt with APIs, you'll want to stick around for this. Imagine you have an e-commerce site. Your customers are happily clicking away, adding items to their carts and hitting their sweet order buttons. Their requests zip through the API gateway and land at the order service, which then passes the baton to the payment service to handle the transactions. This is where external payment service provider, or PSP for short, comes into play. Let's call our PSP Stripe. So how does Stripe communicate with your website to confirm that the payment is good to go? Traditionally, we'll use what's called short polling. It's like repeatedly asking, "Are we there yet?" on a long car ride. After sending the payment request to Stripe, your payment service would keep checking in. "Is the payment ready? How about now?" And this would go on until Stripe finally said, "Yep, all good here." But hold on, there's a catch. Short polling is like a needy app that's always asking for updates. It can be a bit of a resource hog. What about long polling? Think of long polling as a more patient sibling of short polling. Instead of constantly asking for updates, the server holds the request open for a while and only responds when there's new information. It's better, but still not perfect. You're waiting on the line, and it can be tough on server resources. Enter webhooks. Instead of bugging Stripe for updates, you simply say, "Hey, hit me up at this URL when you've got news." Once Stripe processes the payments, it makes a beeline to your specified URL to drop off the status update. No more wasted resources and constant nagging. You might hear folks call webhooks reverse APIs or pushed APIs, since the server is reaching out to the client with info, not the other way around. But to keep things running smoothly, here are some best practices to follow. 1. Have a fallback polling mechanism in place to detect failed deliveries. Things happen, servers go down, so having a periodic polling mechanism as a backup ensures you don't miss critical updates. In our example, what if Stripe forgets to call? Have a housekeeping job that checks in every so often, just to make sure everything's on track. 2. Secure webhooks with secrets and tokens. You don't want just anyone calling your webhook endpoint. Requiring authentication tokens help prevent abuse. Verify each call signatures to ensure it's really Stripe on the line, not an imposter. 3. Make webhook idempotent. That means code defensively, so if a webhook is delivered more than once, it doesn't cause issues. Include unique identifiers to dedupe whenever possible. 4. Watch out for webhook overload. If you suddenly get popular, can your infrastructure handle a surge in webhook traffic? Plan ahead. For high-volume websites, use queues to decouple the receiving and processing of webhook events. When your site goes viral, you're ready for the spotlight. And webhook may not be the answer when real-time data with microsecond latency is absolutely essential. For the most time-sensitive applications, a persistent socket connection enables push updates with lower overhead than webhooks, but it's more difficult to set up and scale. However, the performance is better. There are definitely trade-offs to consider, but webhooks unlock big efficiency gains when Today we're going to talk about caching, a key concept in system design that is critical. Have you ever wondered how major tech giants like Google and Facebook manage to keep their mountains of codes in check? Or perhaps we're deciding how best to structure our own project's code. The way we manage our code can make or break the team's productivity and the product's stability. That's why today we're diving into the great debate, monorepos versus micro-repos. Before we dive in, did you know that the monorepo concept isn't new? Both Linux and Windows were created using a monorepo approach. Let's start with